Hello. The purpose of this video is to demonstrate how we can use the concept of inverse to solve virtually any simple equation as long as we know what operation we're doing and we know how to undo that operation. So I got 6 examples for you, all to show how the concept of inverse can be applied depending on what it is we're doing to a number. This first case is a really simple example. We've seen it before. Simple algebra 1 kind of thing. If 2/3 times a number equals 4, what was the number? First, thinking about the question, I have to take 2/3 of a number, I should be getting a bigger result. But now let's talk about the procedure. What I'm doing to x is I'm multiplying it by 2/3. My objective is to undo multiply by 2/3. So I'm going to consider the concept of inverse. The inverse of multiplying by 2/3 is dividing by 2/3. Multiply and divide are inverse operations. But instead of dividing by 2/3, we learned in arithmetic that you could multiply by 3/2. So 3/2 is equivalent to, multiplying by 3/2 is equivalent to dividing by 2/3. So in my equation, I'm going to multiply both sides of the equation by the inverse of multiply 2/3, which is multiply by 3/2. On the left-hand side, we can see everything divides out to 1, which is why it's an inverse. And on the right-hand side, we can see 6. Which is bigger than 4? 2/3 of 6 is definitely 4, so it all makes sense. Just to verify using technology, of course, we take out the old Desmos or graphing calculator, and we can see the intersection of y equals 2/3 x, that's the green line, and then the line y equals 4, which is the blue line, they intersect when x equals 6. And as we can see, the left side is y equals 4, which is what we wanted to have over here anyway. So that's a simple example. Let's see some more interesting functions, like the absolute value of x equals 4. I don't know that this is more or less interesting, but the issue here is how do we make the absolute value of x go away, just like we made the 2/3 go away. To figure that out, we have to understand the definition of absolute value. Absolute value says if x is already positive, leave it alone. So right here, if x is already a positive number, then the absolute value does nothing. And here it says if x is a negative number, then the absolute value says take the opposite. So in order to get rid of the absolute value here, we need to consider two possibilities. If x was a positive number, then I leave it alone, I can get rid of the absolute value. Or if x was a negative number, then I need to take the opposite of that negative number, and that will give me 4 as well. Just finishing that up, x is negative 4. So we see two solutions. Graphically speaking, we can see here that they're both negative 4 and positive 4 when the absolute value graph intersects y equals 4. And that's pretty basic. But the lesson here is, again, to make absolute values go away, we need to consider both possibilities, and those will give us both solutions. Now to look at this just one step further, we can see how this definition ties into my two solutions. For starters, if x was 4, and since 4 is less than 0, then the absolute value of 4 is 4. In other words, leave it alone if x is already positive. Our other solution was x is negative 4, which is a little typo there. Let's see if I can put that back. Oops. 1 second. There we go. Good enough. And if x is negative 4, then negative 4 happens to be less than 0, and therefore my absolute value instructions are to take the opposite of negative 4 to give me the positive 4. So we can actually see then how the two parts of the definition play out in doing our algebra. Once again, we see it on the graph. So finally, or not finally, next example is when we square a number and get 4 as a result. Now, it doesn't take a rocket scientist to know that 2 times 2 equals 4, but just looking at it from the mathematical standpoint, the inverse of squaring is square rooting. And so to undo squaring, let's just, we're going to look at 5, and if you square 5, you get 25. If you take the square root of 25, you get 5. So that's inverse. So we're going to inverse the square of both sides of the equation, and most people would say the square root of x squared is x, and the square root of 4 is 2, and be satisfied with the solution. If we looked at it graphically, however, it reveals that there are actually two solutions to the equation, one of them here being negative. So the question is, I've got my algebra over here saying only one solution. My geometry says there are two solutions, and so the question is, what can we do in our algebra to ensure that we get both solutions? And the answer to the question is absolute values. In other words, when I take the square root of x squared, I have to consider the possibility that x could have been positive or negative, then squared and resulted in 4. So the inverse of absolute value, as we saw previously, both positive and negative opportunities, and here we get both solutions. And just as a reminder down below, we can see here that if you square negative 2, it does indeed become positive, and that leads to this conclusion up top, and that is whenever you take the square root of a variable squared, you should get the absolute value, not just x itself. So remember. Cubing is like squaring, only we multiply one extra time. So it should follow that if the inverse of the square root is the square root, then the inverse of the cube would be a cube root. So that's what's shown here. So just reminding, in case you don't know what a cube root is, I'm looking at some simple examples. Oops, I don't know why that line, should I make that go away? Looking at examples, we got x cubed, or sorry, 2 cubed is 2 times 2 times 2, which is 8. It follows that the cube root of 8 would be 2. If 3 cubed is 27, it follows that the cube root of 27 is 3. And if the 4 cubed is 64, then the cube root of 64 is 4. So just understanding cube roots a little bit there, we understand that cube root is the inverse of cube. So here when we have x cubed equals 4, we're going to take the cube root of both sides, and there we get x equals the cube root of 4. Now that we're going to need a calculator for, but I should be sure that this is going to be less than 2, faux show. Because 2 times 2 equals 4, then something less than 2 times itself should be 4. And that reveals itself on the graph right here. We can see the value of cube root of 4 is 1.587, so I approximate the cube root of 4. And I'm just going to leave this question out there. How come I don't have to worry about the absolute value when I take the cube root of x cubed, and I did have to worry about absolute value when I took the square root of x squared? When do we have to worry about absolute values, and when do we not? So I'll leave that question for the group. Continuing on, 2 more. First one is when we have the square root of a function. If the square and square root are inverse operations, it should follow that the inverse of square root is square. So I'm going to square both sides. That's going to get rid of the square root and give me 16. Next question would be, what about absolute values? But see, neither the x nor the square root of x is going to be negative. It never happens. And so there's no need to worry about absolute values in this case. When you square both sides, don't worry about absolute values. It's when you square root a squared variable that you have to think about this. Either way, we should always look at our graphs to support our work, because here we can see clearly there's only one solution, and that solution is 16. And finally, we've got the reciprocal of x is 4. That's the way I read it. But here you could look at it as 1 divided by x. And the inverse of divide by x is multiply by x. So we're going to multiply both sides by x. X is divide out, and you get 1 equals 4x. And now we're going to do the inverse of times 4, or multiply 4, which is divide 4. And we get x equals a quarter. Consistent with my graph, of course. Now, when I like to check my answer, I'm really looking at 1 over 1/4. And to simplify, I multiply top and bottom by 4 and get 4 over 1. This seems to show that the inverse of a reciprocal is reciprocal. In other words, if 1 over x is 5, then x equals 1 over 5. You can see there I actually took the reciprocal of both sides of the equation, and the truth is still correct. Here, if 1 over x is 1/3, it follows that x is going to be 3. You take the reciprocal of 1 over x, and you take the reciprocal of 1/3, and you have another true statement. That should be pretty straightforward. If 1 over something is equal to 1 over 3, then something equals 3. If 1 over x is 2/5, that means that x is going to be 5/2. So this is a shortcut. The inverse of reciprocal being reciprocal, we can just take if 1 over x equals 4, then the inverse of both sides is x equals 1 over 4. So that's a shortcut you can use. So let's summarize real quick. Each of these different equations was doing something to x, and my way of finding x was to invert each operation. So the inverse of 2/3 is multiplied by 3/2. The inverse of absolute value is positive or negative. The inverse of square is square root. The inverse of cube is cube root. The inverse of square root is square. And the inverse of reciprocal is reciprocal. So we use these operations, and it's going to be considered that this is going to be the basis for which we're going to develop our more complicated equations, and that'll come in the next video. Have a great day.